Hello and welcome to the NPTEL online certification course on microelectronics, devices and circuits. In our previous module, we had seen the basic concept of a MOS based differential amplifier. We also seen the concept of half circuit as applied to MOS based differential amplifiers, and we saw the advantage that a MOS based differential circuit will have as mathematically advantage, because once we are able to find out the voltage at a particular point at a particular for a particular bridge, the opposite of that will be applied to another bridge, and therefore we can easily calculate the overall gain. What we will do now is we will just continue from where we left in our previous discussion, and we saw that this is the differential. So you see, this is basically your half circuit which is in front of you, the differential half circuit which I was discussing with you, that you do have a Q1 which is basically your MOS transistor here, and I apply a voltage VID by 2, where VID is basically the voltage difference, input voltage difference, and RD is the resistance offered, and we get minus VOD by 2 as the output voltage with the negative sign, because it is 180 degree phase shifted. In such a scenario, the overall gain is given as GM times RD parallel to RO, right. And let me show you how this works out. So if I have got two circuits here, right, and they are primarily given like this, this is plus VID by 2, this is RD, and then this is again the same here. So there are two half circuits which is here, and then we have got this is the series resistance of the device itself. So this is RO, this is RD, and this is again this is V0 output voltage which we try to find out, and this is minus VID by 2. So you see V01, which is this one V01, this is the output V01, right, and this is V02. So V01 will be, if you want to find out, will be minus GM times RD parallel to RO multiplied by VID by 2. Similarly, VO2 will be equals to GM times RD parallel to RO into VID by 2. So it would have been minus, but since this is a minus sign already available into the input of my input signal, input signal, minus of minus becomes plus, and I get this into consideration. Therefore, output voltage VO will be equals to VO2 minus VO1, and this comes out to be equals to GM times RD parallel to RO multiplied by VID, and therefore VO by output by VID is nothing but GM times RD parallel to RO. Now of course, as you very well know that my RD will be RO is much larger as compared to RD, and therefore for all practical purposes the gain will be equals to GM times RD. In reality it is GM RD parallel RO, which is this is the basically the parallel resistance which you see, because we have assumed, or we know that RD is much smaller as compared to RO, right, and we get that into consideration for all practical purposes. Now with this knowledge, we therefore see that, now let me put the same concept, we will do the same concept here and explain to you that for a common mode signal, for example, for a common mode signal, let us see what happens. For a common mode signal, I need to find out CMRR now, and therefore what I will do is I will just take two RSS. This is with the current source, tail current source, remember. So I have divided into RSS by 2, because when you take in parallel, this 1 by 2 RSS will give you just RSS as the output voltage, because they are in parallel with respect to each other. So assume that I have given VICM here, I have also given VICM here, this is RD, and then I have put across this concept here, and then try to find out the output voltage here. So this is V01 and this is V02. So if you want to find out the output voltage, so this is basically my half circuit here. So why is it RSS by 2? Because we have divided into two parts and we got RSS by 2 as the overall signal. So if I find out V01 by VICM, this will be equals to V02 by VICM will be equals to minus RD upon 1 by GM times 2 RSS. Why? Because you remember, one of our previous discussions we had seen that if you want to find out the gain the output voltage gain just by inspection, then you just have to do one thing, that you divide the whole thing into 2 such that somewhere in the middle the device is in the middle, and this is the output profile and this is your grounded profile. So, when you go from this side to this side, you just check out how much amount of resistance being offered in the line below this dotted line. It is 1 by Gm, because when you look from the source side into the MOS device, the resistance offered is 1 by Gm, and series to that is 2 RSS. So, the denominator is therefore 1 by Gm plus 2 RSS, and from top, if you come from VDD, which is the grounded here, I get RD as my output. So, I get minus RD upon 1 by Gm plus 2 RSS as my value. We already know that RSS is much larger as compared to 1 by Gm, and therefore, I can safely write down V01 by Vi Cm equals to V02 by Vi Cm. This is common mode signal to be equals to RD upon, right, 2 times RSS, because Gm is much smaller and I can neglect that value here, and I get RD by 2 RSS as my overall picture. So, let me find out common mode gain therefore and make it mod. I get RD upon 2 RSS, and I get AD, which is the differential mode gain, to be equals to 1 by 2 Gm times RD. Why 1 by 2? Because now you see I am trying to find out for a single circuit. So, that is the reason it is not GMRD, it is GMRD by 2. If it would have been differential, you multiply it by 2 and you get GMRD, right, and therefore, I get CMRR, which is common mode rejection ratio, to be equals to AD by ACM mod of that, and if you try to find out this overall picture, I get Gm times RSS. And since RSS is relatively very high, because you are using a tail current source which is assumed to be an ideal current source, RSS value is very high, and therefore, CMRR happens to be very high, 10 to the power 5, 10 to the power 6 orders of magnitude. So, with this knowledge, what we have understood therefore is that if we do have a differential or a common mode signal, the common mode signal will give you a large value of CMRR. Now, let me just give you a brief insight into one important point which needs to be looked into, and let me see whether we can maybe I can explain to you in this case, right. What we were doing is that we were actually looking into 2 important facts, that whenever you do have let us suppose I have here device and we have another device here, and then we have a current source which is here. So, rather than taking differential output, we can also take a single ended output, then your gain falls by 2, but you get a differential, you get a single ended. This is known as a differential to single ended output converter. So, from a differential input, I am giving a differential input here, VID by minus VID by 2 to plus VID by 2, right, and I am giving this and this, right, and I am trying to find out if it would have been purely differential, I would have found out here, but no, I am only interested in a single ended output, I get this. So, you will see that, and you can do it yourself by doing small manipulation and small derivation, that this primarily will be giving you twice lesser gain, approximately 6 dB less gain will be there if you do a single ended operation, right. If you do a single ended operation, you will get VID by 2 as a single, sorry, you will get 6 dB less gain in a more so in a different manner. And second cost you pay for it is of course your you do not have your common mode rejection is not very good, right. So, this is one of the problem areas which people faced when we were doing a differential amplifier to single ended amplifier. With this knowledge, let me therefore explain to you the various other factors that when you do a differential amplifier with the current source load. So, what happened was that with this large your gain, you have a large gain available with you, differential it also rejects noise as we discussed, common mode signals, but if you go back to your previous discussions and understandings, you will see that we did have a RD here, remember we had a RD here. So, I have a voltage source, I have a RD here. Now, this RD is generally realized what are known as, so these are known as passive loads, because you are putting a resistance here, right. We also have what is known as an active load. Active load means a MOS device acting as a resistor, that is known as an active load. So, most of the time what we try to do is we try to insert in place of RD, which is a passive load because of its high power dissipation, we try to insert an active load, right, and this is one of the examples of the active load which you see. So, also known as a current source load or active load. So, what I do is I give a gate voltage here, and these are basically your PMOS device. So, these are on NMOS and these are PMOS devices, right. These are PMOS devices, and if you give a gate voltage here which such that it is lower the threshold voltage of the device, switches it on, keeps in the triode region and starts working as a diode. So, what is the VDS value here? The difference between VDS value is VD, this is connected to VDD. So, VDD, let us, if we talk of Q4, then VDD minus, let us suppose this is let me say source V source of 4. So, I get VDD minus Vs of 4 is nothing but V ds of 4, drain to source of 4, right, you see here, and therefore, gate is Vg and minus Vs4, this is gate to source voltage. If you subtract this, because if you remember what was the condition, Vds should be greater than equals to Vgs for an NMOS, right, and should be less than equals to Vgs minus Vth for PMOS. So, I get Vg, so if you find out Vgs is gate to source is Vg minus Vs4 is gate to source, right. So, this is your gate to source minus threshold voltage of the MOS device which is Q4, right, and this should be greater than equals to Vds, which is nothing but Vdd minus Vs4, right. If you look very carefully, these two will get cancelled out, Vs4, I get Vg minus Vt should be greater than Vdd for this device to be staying in saturation, right. So, once you are able to sustain a large value of Vg such that so if your Vdd is say 2 volts and threshold voltage of these devices are 0.7, then you have to at least give 2.7 voltage at the gate side to make them behave as on state devices, and they will be acting as a resistors here, right. So, these are active load devices also which are there with us. Now, I will explain to you what about sorry. So, what we will do here, so this is what you get. Similarly, in a PMOS I can do one more thing, that this Q3 can be actually grounded. So, if you ground your MOS device and if your drain voltage is already grounded here, which is drain is grounded here, then and your gate is also grounded, then gate to source is this one, right, will always be negative value, and therefore, it will always make your Q3 on state, and therefore, it will all behave like a pure resistive domain architecture, and will give you VOD by 2. If I give a VID by half circuit concept, so if I give VID by 2 here, I get VOD by 2 in the output side, and therefore, I get AD equals to GM1 into R01 into parallel to R03, which means that the overall differential mode gain is depending on the transconductance of the input transistor. So, these Q1 and Q2 are referred to as input transistors, right, input transistors, whereas Q3 and Q4 are referred to as loads, in this case active loads, right. So, they are referred to as active loads, and this is therefore, when you do R01 parallel to R03, because if you look carefully, this R03 is here, R03, and you have an R01 here. So, since these two are in parallel, the effective load seen by the Q1 will be R01 parallel to R03, and you can automatically therefore gauge the value of drain voltage in the output side. Another method which people adopted and it's still being adopted with certain disadvantages, of course, is what is known as a cascoded differential amplifier. So, what we do is your Q1 and Q2, which is basically your driver transistors, they are NMOS devices driven by VCM plus VID by 2 and VCM minus VID by 2, as we discussed earlier, and we have a current source here. But what we try to do is in the pull up state, in the higher state, we try to have large number of devices in stacked, so in a cascaded fashion, so that the overall gain can be increased higher and higher, because you will have so much large number of devices in parallel with respect to each other. Therefore, I get in this case to be equals to GM1, which is again this one, into R on is basically RO, output resistance of NMOS, which is this one, and then parallel resistance of gives you ROP. So, GM1 into ROP into RON is effectively a value of AD. So, if you look at the half circuit concept once again, I can ground these three, small signal analysis, give a VID by 2 here, and I get ROP equals to RON, which is RON equals to this much. RON is and ROP is what? ROP, if you look very carefully, is basically looking from this side, if you go up. So, you will always have RO7 and RO5 in series. So, GM5, so you see GM5 into RO5 is nothing but the current flowing through the resistance through the MOS device Q5 current, that if you multiply with RO7, which is basically the parallel impedance, then we get automatically the value of this thing. So, if you remember when we try to find out the resistance, it is basically the small signal resistance square which we are trying to find out, right. So, RO is nothing but the square. So, if you see ROP is proportional to RO5 into RO7, which is basically, if I assume that them to be equal, I get RO square. When you do therefore triple cascode, I will get RO3, RO cube, sorry, and RO, similarly RON will be proportional to RO square, because there are two transistors in series to each other. So, Q2 and Q4 are in series and they are NMOS, and therefore, I get this much. Similarly, Q5 and Q6 and Q8 are again in series, and I get GM3 multiplied by R0 square. So, what I get is RON is equals to GM3 multiplied by R0 square. I get ROP to be equals to GM5 multiplied by R0 square. And therefore, simply by choosing a higher value of GM3 and GM5, I can actually manipulate the overall resistance or the overall gain of the system. If you look very carefully, therefore, that we have discussed in the earlier phases that common mode gain will be always 0 and your CMRR will be always infinitely high. So, ACM will be approximately equals to 0, and your CMRR, we have already discussed this point, is ideally should be equals to infinity, right. And that is what I have shown here, that if you have VICM, I get this, and if you do a design, then what I do is I make it RSS, assuming that both the currents are I1, I is current flowing, I get 2I current flow here, and therefore VOD will always gives you a 0 value at the value of common mode signal. Now, let me therefore, as I discussed with you just now, and I was deriving also with you, that do a half circuit here. Remember, I can remove the MOS device here and show it as a current source in series with 1 by GM. Remember, because looking on the source side, the amount of resistance offered is actually equals to 1 by GM. So, I simply do a series connection between the current source and 1 by GM, current source and 1 by GM, and then I 2 RSS, because 1 by 2 RSS plus 1 by 2 RSS in parallel will always give you RSS value in more respect, and that is the reason when you do a half circuit, I get 2 RSS VO1 RD, and then I get 2 I by 2 current is flowing within 2 ohms, right, and this is what the general scheme of things are. Now, if you see VICM, as I discussed with you, will be I by GM plus 2I RSS, right, and similarly as I discussed with you just now, that V01 by VCM plus V01 by VSC is RD by 2 RSS. If I assume them to be equal, I get V01 equals to V02 equals to minus RD by GRS. Now, what we did was that 1 by GM is much smaller, and therefore RD is greater than RD by 2 RSS is the value of your output voltage. Let me therefore come to the next stage, an RD mismatch. Let me explain to you what is RD mismatch. See, what was happening till now was that all this discussion was with the assumption that there is no mismatch of the resistances and the transconductances of the device used in the left arm and right arm of the differential amplifier. They are perfectly symmetrical, and therefore all the common mode signals were lost and all the differential mode signals were magnified. In reality, not true. When you actually fabricate a circuit, you will always have a mismatch of the resistors. which means that you cannot have a fixed value of resistor always available with you, they will always vary with each other. So let us also come to the point that if there is a mismatch in the drain resistance for example, then how does it influence my common mode rejection ratio. If you look very carefully, V0, if this is mismatch, as I discussed with you, it is basically RD by 2 RSS. Remember, we just now saw V01 is equal to RD by 2 RSS, and V02 will be equals to RD plus, let us suppose, del RD by 2 RSS into VCM. So we are seeing the effect of V in del RD on VNCM. So if you VOD will be output difference is V01 minus V02 comes out to be this value, right, and therefore ACM is basically, so what I do is I put it into denominator, and therefore I get ACM is equal to del RD by 2 RSS. So CMRR is how much, will be equals to 2, because if you remember this will be this 2 you had, so you will get del RD by 2 RSS, so you will get GM times RSS divided by del RD by 2 RSS. This 2 RSS will go to the top and you will get this value of CMRR, right, you get GM RSS. So you get this into consideration, right, and so for what, how much you get 2 times GM times, right, RD by del RD into RSS as your CMRR. Now if you do a GM mismatch, which is transconductance mismatch, let us see how it works out in that sense. So if you do a transconductance mismatch, let us suppose I have got ID1 to be equals to GM1 VGS1 and ID2 to be equals to GM2 VGS2, right, and if I assume that VGS1 is equals to VGS2, then I get ID1 by ID2 to be equals to GM1 by GM2, and therefore I get Vs, which is the source resistance, to be equals to ID1 plus ID2 multiplied by RSS, and therefore I get ID1 plus ID2 to be equals to Vs by RSS, right. Now Vs is nothing but VICM because that is the voltage difference between the two, and therefore I can write down, because why, because Q1 and Q2 are basically source followers. So whatever value of voltage you are giving on the gate side appears across the source side, so the difference between them is always almost equals to 0, and therefore I get as this thing. So I get ID1 equals to GM times VICM upon GM1 plus GM2 divided by RSS, and I get ID2 to be equals to GM2, so this is GM1 into VICM upon GM1 plus GM2 divided into RSS, right. Now if I assume that GM1 is and GM2, the difference is very small, then I can safely write down GM1 plus GM2 is approximately equals to twice GM. So I can write down twice GM here, and assuming that del GM is very small, it is not 0 but it is very small, so it's relatively very small, right. So if you get this into consideration, or you get this into idea, I can write down, right, I can write down ID1 to be equals to GM1 times VICM divided by 2 GM times RSS, and ID2 to be equals to GM2 multiplied by V in CM divided by 2 GM times RSS. So I get V01 minus V02 minus V01 is equals to minus ID2 RD plus ID1 RD. So if you solve it, I get RD ID1 minus ID2, which is nothing but delta GM times RD upon 2 GM RSS multiplied by V in CM. So if you take V in CM in the denominator, I get VCM equals to RD by 2 RSS into delta GM by GM, right, and since already we know that AD equals to minus GM times RD, I can write down CMRR to be equals to AD by AC, which is nothing but 2 GM times RSS divided by del GM by GM, right. So this is the overall CMRR which we see when we have a GM mismatch, right, and this GM mismatch therefore depends upon the value of your del GM. So when your del GM is typically very large, right, that tends to lower your CMRR, right. So, if your mismatch is more both in terms of RD or GM, it lowers your CMRR, and the reason is very simple. Why does it lower it? Physically also you can understand, because then the common mode signal itself gets differentiated and gets amplified, and therefore the differential amplifier is not able to distinguish between a differential mode signal and a common mode signal, because both of them look the same to the differential amplifier, and therefore it equally amplifies both the signals together, right. And that is the problem area which people face as far as mismatch is concerned. So, let me recapitulate what we have done till now, and let me see what we will learn in the further. That any small signal circuit analysis where we assume that the transconductance is always there for a device which converts a voltage into a current source, we will be able to calculate the differential gain, common mode gain, and the common mode rejection ratio. These three are very important. In fact, these two are very important. Automatically this is the third one which comes out of the difference between the differential mode and common mode gain. As we saw that CMRR will obviously be a strong function of the output impedance, the reason being higher the output impedance, larger will be the gain, differential mode gain, and as a result you will get a larger CMRR in that sense. How can you increase it? By you can increase the common mode, you can increase the CMRR by increasing the output resistance of the current source, which is very true also. More ideally your current source is, better your CMRR is, because you ensure that your source resistance of the MOS device is infinitely high, which is typically very high, and therefore it sort of acts like a virtual ground, right. Virtual ground means though it is grounded in a sense, but there is the current is not flowing out of that particular arm. And as we also saw that CMRR can be increased if I do a cascoded amplifier, which means that I cascode devices one top of each other, stacking the devices. As a result my overall output impedance increases, and therefore my gain also increases, or overall gain increases, which means my differential gain increases not at the cost of the common mode gain, and as a result my CMRR goes to a very high value, right. This we have learned through large number of simulation tools, through large number of understanding. We have also understood that this RD mismatch and GM mismatches will lower your CMRR, and it will not improve your CMRR, and therefore from fabrication point of view one has to always entertain, or one has to always see that you always have the perfectly symmetrical arms available to you. Most of the time not available, then my CMRR falls down from a large value to a relatively small value, right. So, lower your mismatches and try to make the GM of the input devices and the output impedances to be too large in order to increase the CMRR and therefore reject the noise, right. With this let me thank you for your patient hearing, and we will discuss other topics in the upcoming tutorials and slides. Thank you very much.